Okay, so if a square
Monday.
let's see, okay, it's cubed, then it goes 1, 2, 3.
Okay, so he
Does
doesn't
that make sense?
Yeah, he
That's
doesn't.
how I learned it.
Oh, that's smart. Okay, yeah, tomorrow for sure.
So basically, just looking at, I don't know, do you have a graphic calculator?
I don't want to use it, but I don't want to read it.
Yeah. So sometimes you can also try doing like a Google search, just type in the equation if you can't figure out how it's supposed to look. There are sites that will show you.
So, on Monday, we were talking about transformation of functions. We take a function and we do something to it, we move it around. We talk about shifts, vertical shifts, horizontal shifts. So if I take some function f of x and I add a constant, that just takes the function and moves it up along the y-axis, right? If I subtract, it moves it down. That's a vertical shift. Horizontal shift, take my function and let's say I add something to the independent variable. Well, that's a horizontal shift, but which way does it move it? If I add a positive number, which way does it move it? Counterintuitive. Moves it to the left. Right? I mean, adding here moves it up, but this does not move it to the right, it moves it to the left. Something to not forget. We talked about reflections. It's where you take f of x and make it negative f of x. That reflects it over the x-axis, right? So positive y becomes negative y, and so forth. The x-axis. The y-axis, you take the independent variable and change its sign. Well, that's not what I wanted to write. I wanted to write this. It's my transformation. That's going to reflect it across the y-axis. And of course I could do both. I could take f of x to minus f of minus x. That reflects it both the x-axis and the y-axis. The result is you get a reflection over the origin. Okay, so that's where we're going to start. Yes?
You'll be able to put that down on your podium.
X and Y origin. Is that what you want?
Well, no, I was asking if you could put the thing on your podium down. So.
Oh. Okay.
Thank you.
I'll have to put it up later. You know, it's weird. The other room, I'm in the other room opposite this. It doesn't do this. It's weird. It doesn't get in people's way. So I don't know. Maybe move this. All right. All these transformations have something in common. If you remember back to geometry, we had the idea of say, two triangles that were congruent, right? They have the same shape. Well, when you do these transformations, the functions have the same shape. I guess you could argue when you reflect, you know, it's not symmetric. Yeah, but it's a reflection. It's the same shape. It's just, you know, looking from the other side of the blackboard. If you just go to the other side of the blackboard, you'd see it's the same. But it doesn't change the size any. And now we're going to look at some transformations that do just that. These are called dilations. And the book talks about stretching and shrinking. Stretching and shrinking are just two words incorporated in a dilation. So, how do we do this? Well, I guess I just don't write below a certain point over here. I guess that's how I have to do it. That's fine. So if I take f of x and I transform it to some constant times f of x, where c is greater than 1. Okay? So for each value of x, I'm going to get a new value which is just multiplied by c. And I have to go back and show you what that might look like. Oh, it's not what I wanted. It was, it's amazed how, like, when you do something a lot on a computer, your hands learn how to do it without your brain being attached. Anyone ever notice that? If you haven't, you will. It's creepy. I mean, if it's what you wanted to do, you're like, wow, that's great, I'm so smart, but do something different. Turns out different. Okay. So, let's take this function, x cubed. I'm going to change it a little. 0.5x cubed minus 0.3x squared. Okay. You get the benefit of, I tried this last time and it didn't look as good. All right, so let's see what happens when I take this function and I'm going to multiply it by some factor. So we'll say 2. Okay, so if you look here, you'll see that now the maximum that was up here now is like jumped up. We multiplied it, so that whatever that point is, it's twice what this is. Same thing with the minimum. It's now jumped down to here. I guess I have to, there we go, mark the right one. And each point along the function, the same thing has happened. I've multiplied each point of the function by a value. So this is a stretch transformation. I'm stretching the function up along the y-axis. Okay. If c was less than 1, expected to do kind of the opposite, right? Let's see that. Yeah, okay. So now, now each of these points is now half of what their value were, except for, say, the zeros, you know, 0 times something is 0. Everything's moved. So that's one way to transform a function. Again, that's in the y-axis direction. We'd like to know now what happens if we do something like that, but instead of multiplying by the function, now we're going to multiply by the independent variable. You would think, possibly incorrectly, just like when we were talking about translating, right? How when you add to the independent variable, it goes in the other direction, you might have thought right away. The same type of thing is going to happen here. Let's get rid of this. This is a little trickier to input. So let's say 2x cubed, really x cubed, and 2x squared, and 2x. All right, let's see what happens.
The cube is inside, the square is outside.
I made a mistake. Yes. Oh, yes, thank you. Nobody rescued me in the other class. All right. What am I doing wrong here? 2x, 2x, 2x. Say once more? No, I'm
You're forgetting your exponent on the first 2x.
that is. Ah, okay. It didn't want to show me anything because I had a boo-boo. Okay, all right. This is what I wanted to look at. So what happens now? In case it wasn't clear, this is, okay, that's the original function. I multiplied the independent variable by 2, but what's happened? All the, you know, this 0 you can see moved in here. This minimum moved over here. Everything got squeezed together, right? So this is something you have to remember. It's a little counterintuitive. When you take a number greater than 1 and put it here, what happens? Squeeze it together along the x-axis. You might expect that if I use a number less than 1 here, like say 1/2, it's just easier to decimally. There we go. Just the opposite happens. Now it stretches it out. Okay? So again, it's counterintuitive. This is important. This will come up quite a bit. And now we're taking functions. We no longer have congruent functions. We've changed the shape. Okay. Any questions about? We're done with transforming functions for the moment. It's not going to go away though. So. The next topic is a category or a classification of functions. That's very important. We've kind of seen examples already, and we've kind of seen what we're going for, but here we're going to be very specific. We're going to look at even and odd functions. So let me just bring up an example. We don't do that. Let me just put this away. Okay, here's an example of an even function. It's our friend the parabola. So we want to ask what makes this an even function, or rather, what is the definition of an even function? It's very straightforward. An even function is a function where f of minus x equals f of x. All right, that seems almost too simple, but let's apply it here. We have f of x, f of minus x equals what? Since f of x is x squared, it's minus x squared. It's minus 1 squared times x squared equals x squared. But that's equal to f of x. So this is an even function. Okay. One thing to note about the graph of an even function is that it's always symmetric with the y-axis. So each point on one side of the y-axis will have an equivalent point on the opposite side. Let's look at an odd function. What's an odd function? Well, the definition of an odd function is f of minus x. In other words, we change the independent variable, we multiply it by minus 1, is minus f of x. Okay, clearly x squared is not an odd function. We need an example. So let's look at g of x equals x cubed. Right? So g of minus x is equal to minus x cubed equals minus 1 cubed. X cubed equals minus 1 times x cubed equals minus g of x. So g of minus x equal to minus g of x. This is an odd function. What does an odd function look like? Well, let's see. Okay, so here's a function that's now symmetric around the origin. Another way to think of it is we've taken the function, we reflect it on the x-axis, we reflect it on the y-axis, and we get our function back. So these are two very important classes of functions. It's good to know that this naming we've given them coincides with something you're familiar with. You know, for example, if you multiply two even numbers, you get an even number. You multiply two even numbers, an even number and an odd, and you get an even. And it's only when you multiply two odd numbers that you get an odd number. Well, we're going to see the same thing is true of when we multiply functions. If we take two even functions, let's say f of x equals x squared, and g of x equals x to the fourth. If we multiply these rules together, we're going to get x to the sixth, and some function h of x equals x to the sixth. That's going to be even. Similarly, if we multiply f of x and g of x, where g of x is an odd function, we're going to get, wait a minute, something's wrong here. Something's wrong here. Now I know how I screwed up last class. It's only when someone's watching me screw up. Apparently, you multiply an odd and an even function, you get an odd function. That didn't work right, did it? And if I multiply two even odd functions, like x cubed and x cubed, I get an even function. All right, well, I'm not here on Fridays because I get fired for doing this, so telling students the wrong thing. All right, let's take a look at a problem, an example. Let's take a look at this function. F of x equals x to the fifth plus x. You're going to ask, is this an even or an odd function? Right? So we want to look at f of minus x becomes negative x to the fifth. It's negative x. Negative 1 to the fifth is negative 1, so we have negative x to the fifth plus negative x. We take out a minus 1, at x to the fifth plus x. Well, that's just negative f of x. So that tells us we've got what? Odd function. Okay. Let's try one more, easy one. F of x equals 1 minus x to the fourth. So f of minus x equals 1 minus x to the fourth equals, well, the minus 1 to the fourth is going to go away, 1 minus x to the fourth, that's just f of x. So this is an even function. Does a function have to be odd or even? Like, can a function be neither? Let's take something simple. G of x equals x plus 2. Well, what's g of minus x? Minus x plus 2. Well, that's not g of x, and it's not minus g of x, right? So actually, odd functions and even functions, although we're going to run into them, they're a little unusual. They're very special. They have that symmetry that we talked about. Let me ask a different question. Could a function be both even and odd? Think about that for a minute. What would a function that's both even and odd look like? ideas? I can have sympathy that you're not in observing mode, you're not in thinking mode, right? On Monday, you're not in observing mode, you're in thinking mode. Exam, right? Well, okay. Let's see, what would that mean? So, if it's even, so then f of minus x would equal f of x. But if it's odd, f of minus x would equal minus f of x. So if it's even and odd, f of x would equal minus f of x. So there's some function where for every point f of x is equal to the opposite of itself. Somebody's thinking, that actually is really, it's almost brilliant, except there's one small problem. It's not a function, yeah. But otherwise, I'd never thought of that. Yeah, that's right. And in fact, it's got both the symmetry, right? Okay, we're getting close. Well, we could have what we call a degenerate circle. Just have a point here, right? This is a pretty meaningless function, right? F of 0 equals 0, and the domain is just 0. That's an odd even function. Not much to it. We could do just a little better, though. Isn't there a little better function than this? It's not a good function, but it's a little better. See, if let's say I substitute this here, like you say y, so y equals minus y. Y equals minus y. What does y equal? Let's find out. Let's add y to both sides. That's 2y equals 0. And divide by 2, right? Y equals 0. That's the only way to get a number that's equal to its, its multiplicative opposite, right? So any function, well, you need a symmetric domain, right? Like you could have this f of x equals 0. The domain could be like -1 to 1, or it could be all reals, right? Minus infinity to infinity. That would be a function that is both odd and even. I have another question. Couldn't answer it in the other class, so we just kind of left it hanging. So here we have a function that's got symmetry across both axes at the same time. We've got your even functions. They're symmetric across the y-axis. Could I have a function that's symmetric across the x-axis? Could I have that? Is that possible?
No, because otherwise it wouldn't pass the vertical line test.
Yeah, if you had some function over here that is symmetric, we'd have a problem, wouldn't it? It wouldn't be a function, right? You're halfway there. Or could it? How could we do that? How could we have a function that's symmetric on the x-axis but doesn't have, it doesn't fail the vertical line test? Yeah?
What could it cross the y-axis also? Like have it as 1 and 1 and 1 and 3?
That?
No, like have it negative.
Like that? I realize my drawing here. I'll draw something simple. Okay. All I really want to know is, tell me what the function looks like. Because I'm going to spin it, whatever you give me, I'm going to spin it around the x-axis. Okay, that's all
Could
right.
you do like a transform for Lambda? Will that still be a function?
No. So this is, I know what's wrong. What's wrong is the answer is too simple. We're looking for something complicated. It's too simple. All right, I'll let you guys think about it. We can talk about that on the next day. See if you can think of a function that you spin it around the x-axis, but it's still a function. All right. Okay. Listen, keep this again. So, we're on to a new topic here. We're going to talk about combining functions. Okay, let's start with combining the function. We're gonna have an f of x and a g of x, and we want to add the function to get a new function called h of x. Now, let's be careful. Function is not a number. Right? We know how to add numbers. Maybe you've done matrices, you know how to add matrices. Functions are kind of a complicated thing, so we have to be a little careful about what we mean by this. Well, what we mean is we have a new function h. How do we get its values at an x? Well, f of x has to have a value at that x. G of x has to have a value, and then we add those two together, and we get the value of h of x at that. If you look at this kind of diagram over here, and you remember that function's like a machine. So we have a big machine, we'll call him h, that we give it an x. But inside that machine, we take the x and we give it to f, right? We get out an f of x. We take the same x, we give it to g, and we have a g of x. And we add them together, and that's our output from our new machine, our new function. All right, that's fine. We have a small problem we have to contend with, which is, let's say f of x has a domain of minus infinity to 1. My g of x has a domain of, say, minus 1 to infinity. So, in other words, here's -1, here's 1. One of my domains is like this. Another domain is like this. So what am I going to do to make h a valid function? Well, I have to restrict the domain. I have to say, wait a minute. I can only define x for values where f of x and g of x are defined. That is, I want the intersection of these two domains, which is just this interval from -1 to 1. Okay, that's something we're going to have to look at when we're combining functions. Because at the very least, our new function can only have a domain which is the intersection. Now, sure, in lots of cases, both functions, their domain will be all real numbers. The intersection is all real numbers. You have to think about it. We're going to kind of hide that, when we just write it this way. But it's something you have to be aware of. Okay. All right, let's take a look at some actual functions. Let's look at f of x equals 6x plus 4, and g of x equals x squared plus 4. And we're going to graph those here. We're going to see a graph of those. Okay, and also h of x equals f of x plus g of x. All right, so let's look at this diagram here. F of x equals 6x plus 4. Well, that's a line, right? It's my line over here. Right? Okay, it has a y-intercept of 4, a slope of 6. Looks like I've got a slightly distorted set of scales here. It probably looks steeper. My other function, what's my other function? X squared plus 4. Okay, well, that's this parabola here. No, actually, I'm pretty sure this diagram is wrong. Let me see if I can fix that. Use real time here. So. And the second equation was x squared plus 4. Okay, can you see both of those still? Okay, so now we want to see what happens when you sum these. Okay. So it's just going to be x squared plus 4 plus 6x. Yeah, plus 4. Plus 4. Okay, that looks a little better. So you see here, what we have is we add two functions. One's a line, one's a parabola. And what we get is we get another parabola. Really, it looks just like kind of a translated parabola. There's something about this that makes sense. See, my f of x, this is just a linear equation, but I'm adding it to a second degree equation, parabola. I'm just getting a second degree equation, so it makes sense that it's another parabola. If you think about it, if I add two parabolas, I should still get another parabola. All right, let's move on here. So, of course, if I can add two functions like this, surely I can subtract two functions. And I'm just taking the values of f and g, and I subtract them. And that for each x. That gives me my new function. Again, I still have the same issue with the domain. I might have to restrict the domain. My new domain is just the intersection of the other domains that I'm dealing with. We can do the same thing by multiplying two functions, right? F of x times g of x. Now, this gets a little more interesting because now if I take those the functions we were using, 6x plus 4 and x squared plus 1, well, now I'm going to get a higher degree equation. I'm going to get a third degree equation. All right. Finally, the last thing we could do, of course, is we could divide these functions. We could have h of x as, I'm going to make this g of x over f of x. And again, we create our new function by just taking points and dividing. Now, there's an added wrinkle when you create a function this way. Do you have any thoughts on what we have to watch out for now? Yeah.
How come you put g of x over f of x and not the other way around?
Because I wanted x squared plus 1 to be over 6x plus 4. But I could do it the other way. That's a perfectly good function.
That's just easy.
They're not the same function, right? F of x over g of x is not the same. The reason has to do with the question I was just asking. Because if I had done this, and I have 6x plus 4, x squared plus 1, there's no problem, right? There's no problem because the denominator can never be 0 here, right? But in this example, there is an x for which the denominator is 0. What's that? It's x equals negative 2/3. Well, this value could be in the domain of both of these functions, but it can't be in the domain of our new function. So our new function, again, whatever our domain was, right? If where the denominator is 0, we have to eliminate that from the domain. All right, we're going to see an example of why this is tricky in just a minute. Anybody colorblind and can't see blue? And black is on south of blue. All right, what I want to do, I'm going to define two functions and then combine them and see what I get. I'm going to take, my first function is 1 over x minus 2. And my second function is the square root of x. So I want to know what h of x is, where h of x is f of x plus g of x. So of course it's easy to find the new rule. I can just do that algebraically. That's just going to be equal to 1 over x minus 2 plus the square root of x. Now I have to work a little. So I want to know what the domain of h is. Well, let's start off with f. Domain of f is what? Domain of 1 over x minus 2. What's the domain of that function? Yes? Right, so x, this could be a real, x cannot be 2. Very good. All right, what about g? What's my domain of g? G is the square root of x. Yes?
X is greater than 0.
X greater than or equal to 0. What you said? Good, okay. So now, what's my domain of h here? Remember, it's got to be the intersection of these two. Well, we could start here. We could say, well, x has to be greater than or equal to 0. But what else? Not 2, right? Remember, a function is not just a rule. It's a rule and those values, the domain that you can plug in. We can always restrict the domain to less than what its maximum. But if we're just trying to figure out what its maximum is, we have to look carefully. We have to see where these algebraic expressions are defined. All right. I want to take the same problem, but now I want to look at h of x equal to g of x over f of x. And it's not too hard to figure out the rule. Right? G of x is square root of x. F of x is 1 over x minus 2. So this is just x minus 2 square root of x. Right? But now we have to think about what the domain of this is. I mean, if you just looked at this expression and I said, what's the domain of this expression? You would say, well, it's just x greater than or equal to 0, right? And then you say, wait a minute, what about 2? Oh, I could plug in 2 here, right? So is 2 part of the domain of my function? Well, no. You see, 2 is not part of the domain of f of x. And since we create h of x as g of x over f of x, it's not defined there. I mean, this expression is defined there, but our function is not. So again, we're going to end up with this same domain. This is seems a little odd, and if you're just used to just taking those algebraic expressions and manipulating them and not thinking, you're going to miss this. But this is an important thing about functions. Okay.